One of the things Demoivre's theorem allows us to do is allows us to play with trig identities. There's a lovely little connection because obviously we're dealing in mod arg form, we have cosine, we have sine. We know these results, but here's another way, a nice neat way, using complex numbers of how we can find the result. Right? Because now we can say, well, cos 2 theta plus I sine 2 theta, that would be the same as cos theta plus I sine theta squared. And if I expand the right hand side out, I get that. And now all I've got to do is equate the real and imaginary parts. The real part, cos 2 theta equals cos squared minus sine squared. And then the imaginary part, sine 2 theta is 2 sine theta cos theta. A nice, neat, quick proof of those identities that we recognise. Let's find ones for sine 3 theta. And this is where it becomes quite useful, because now I don't have to worry about using compound angles and saying, well, sine 3 theta would be sine of 2 theta plus theta and that. It comes out quite nicely. If I expand my cubic out, and then again I'll just equate the real and imaginary parts, there's a relationship for sine 3 theta straight away. Bang, we've got it. Yeah, it's probably more normal to see the sine one in terms of sines. I can substitute in for the cos squared, 1 minus sine squared, and we get our identity of sine 3 theta is 3 sine theta minus 4 sine cubed. I could do a similar thing for cos 3 theta. Again, there it is straight away, reading off the real parts. But sine squared, no, let's have it in terms of cos theta. Substitute in 1 minus cos squared, and we get our cos 3 theta relationship. Now that I've got both of those, I can get one for tan 3 theta. Because I'll just substitute into sine 3 theta and cos 3 theta, the two that we've just worked out. There's a relationship. But again, let's put it in terms of tan. I need to create sines on cos. I'll divide everything then by cos of whatever the highest power is there, which is cubed, because that then creates all these tans. See, the first one I've got sine on cos, which is tan, sine cubed on cos cubed, tan cubed, and so on. So we get 3 tan theta minus tan cubed theta on 1 minus 3 tan squared theta. But now we're going to show that the cos of pi on 9 is a solution. Now, I can't simply substitute in, which shows something as a solution to an equation. That's what we would normally do. Problem is, we don't know the exact value for the cos of pi on 9, so a bit hard to substitute that in and get an answer. It's not good enough to substitute in and then type it into the calculator and go, oh look, my calculator told me it was 0. That's going to get you no marks. Okay, that's not what we've got to do. So we're going to play around with this. There's the equation. Now I notice a relationship here. See this 4x cubed minus 3x I've created. Why did I do that? Because if I let x equal the cosine of theta, there's that relationship we just proved, is cos 3 theta. I can now turn this equation into a very simple trig equation. Cos 3 theta equals a half. Solve that. Now because it's a cubic, I know I want 3 solutions. So pi on 3, 5 pi on 3, the next solution would be 7 pi on 3. Divide each of those by 3, and I have pi on 9, 5 pi on 9, 7 pi on 9. I think we have to be careful with these sort of questions. Because I'm solving a polynomial here, is are there double roots and things like that? Because if there are no double roots, and this one doesn't have a double root, then I know I need to require 3 consecutive unique solutions. So imagine I'd substituted in and ended up with an answer of 17 pi on 9. Well, that would give me the same answer as the cos of pi on 9. It's not unique. It doesn't give me a different solution. So there is a little bit we have to be careful about. Is there a double root? In this case, there's not. There are my 3 solutions. So in fact, yes, cos of pi on 9 is a solution to this equation. But now they want us to work out this. Cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. We just found that these are the 3 roots of this polynomial. Therefore, I know the product of the roots of this polynomial is 1 on 8. So those 3 things multiplied together must be 1 on 8. Not quite what we want, but very close. I've got the cos pi on 9, I've got the cos 5 pi on 9, but I've got cos 7 pi on 9. Right? Well, that's where we just play around with cosine. We know the cosine of 7 pi on 9, that's in the second quadrant. It would be the same as the cosine of the acute angle, which is 2 pi on 9. Therefore, we must get negative 1/8, because this cos 7 pi on 9 is the same as minus cos 2 pi on 9. This little relationship here, very nice. Z to the power of n plus 1 on z to the power of n, and z to the power of n minus 1 on z to the power of n. The other thing to notice, z is cos theta plus I sine theta. That means its modulus is 1. And when you're talking about reciprocals of complex numbers, if the modulus is 1, the reciprocal is the same as the conjugate. So that could be another relationship here. But anyway, this is what they've asked us to prove, or find, I should say. All right, z to the power of n using de Moivre's is cos n theta plus I sine n theta. And 1 on z to the n, which is z to the negative n, cos negative n theta plus I sine negative n theta. Well, I'm not going to leave it like that. I'm going to play around with our odd and even functions. And so cos of minus n theta is the same as cos n theta. Sine of minus n theta is minus I sine n theta. Right? So remember, because cos function, well, is an even function, so cos of negative x is cos of x. Sine is an odd function, so sine of negative x is the same as negative sine x. Well, if I add these two things together, then the imaginary parts will cancel and I get 2 cos n theta. If I subtract, now it's the real parts that are cancelling, and I get 2I sine n theta. Those relationships there can be very handy to know. Unless, of course, they ask us to prove it, then we'd have to actually go and prove it first. But if they don't, then it's fair enough to just use it. It now allows me to do something like this. Express cos cubed theta in terms of cos multiples of theta. So rather than finding formulas for the cosine of multiples of theta, which is what we did before, we found cos of 2 theta, we found cos of 3 theta, it's the other way around. Now it's the power. How can I do it? Well, 2 cos theta to the power of 3 then is the same as z plus 1 on z cubed, because 2 cos theta would be z plus 1 on z. On the left-hand side, I'll just change that to 8 cos cubed, but the right-hand side, I'll expand it out. Because of the symmetry of the binomial theorem, you get a lovely little pattern there. If you group things with the same coefficient, I've got two things there with a coefficient of 1, which is z cubed plus 1 on z cubed, and I've got two things with a coefficient of 3, z plus 1 on z. Now have a look inside of those parentheses. They match the pattern that we just proved up here. It's z to the power of n, well, the first one where n is 3, and the second one when n is to the power of 1. So therefore, I now know 8 cos cubed must be 2 cos 3 theta for the first one, but then 3 lots of 2 cos theta for the second one. All I've got to do now is divide by 8, and I've got a relationship for cos cubed theta. So 1/4 of cos 3 theta plus 3/4 of cos theta. 3b.